The integrating factor method. In order to use the integrating factor method, we must have a linear first-order ODE in the form of dy dx plus p of x times y equals g of x. Now we multiply the ODE by some function of x, mu of x. Now distribute mu of x throughout, and then we need to make an assumption. In order to get this method to work, we need to assume that mu of x times p of x equals mu prime of x. This assumption allows us to write the ODE like this. We can further simplify this by applying the product rule. U times v prime equals u dv plus v du. If instead we use mu and y, we get mu y prime plus y mu prime, and we can rewrite this as mu of x dy dx plus mu prime of x times y. This is the form that we have so far, which allows us to rewrite this as mu y prime equals mu times g. Now we integrate both sides, and here we can apply the fundamental theorem of calculus, which tells us that the integral of the derivative of a function is just that function, leaving us with this equation. We can rearrange to get the following for y, but don't memorize this formula. When using the integration factor method, follow the process we've used for the general case. I will go over the process in another video with an example, but for now we need to derive an expression for mu of x. In order to determine mu of x, we need to remember our assumption from before, that mu of x times p of x equals mu prime of x. From this equation, we can determine what p of x is. Now, we can look at something familiar. We can take a look at the derivative of the natural log of x. It takes on the same form as p of x. So we can conclude that p of x equals the derivative of the natural log of mu of x. Now we can integrate each side and apply the fundamental theorem of calculus just as before. And now we are left with the integral of p of x dx equals the natural log of mu of x plus an arbitrary constant k, which we will move over to the other side. And now we can exponentiate each side. After exponentiating, we need to apply the exponent rule x to the a plus b equals x to the a times x to the b. This allows us to say that mu of x equals e to the k times e to the integral of p of x dx. E to the k is still an arbitrary constant, which means that we can go ahead and rewrite e to the k as an arbitrary constant k. K will cancel when distributed, and we can see this if we take our results for mu of x and y of x and substitute mu of x into y of x. We will end up with k in the denominator and a k in the integral. We can bring the k out of the integral because it's a constant, and cancel both k's, leaving us with mu of x equals e to the integral of p of x dx.